Hello everyone, welcome back again. So let's see some example of graph in our real life. Okay, so which real life problems we can visualize with graph, or we can represent them using graph. So a graph means actually wherever there is a network, we're going to need graph to represent them. So one example is, let's say, transportation network. So flight, road, or any kind of transportation network means that we're going to have few hub, and where we have to represent whether there is connection from one place to another place. For example, in flight network, in flight network means it's a collection of airport. Okay. All right. And we might want to see whether there is a flight between one airport to another airport. Okay. So for example, like from, let's say A1, A2, A3, A4, their list of airport. Whether there is a flight from A1 to A2, we can represent them as an edge from A1 to A2. All right. Now, road is also same. If we represent each of this intersection as a node, okay, we can say that this intersection has a connected road from this point to that point. Okay, so whenever there is a network, all right, network means actually list of object, all right, and if there is a connection, or if there is a action or connection between two pair of node, we can represent them as a edge between the pair of nodes. Okay, so in transportation network is an example of where we can represent them or visualize them as graph. Communication network. So communication network, let's think about like phone call. Okay, so if we think about like phone call, who calls who? Okay, so who calls who, who is connected, who is communicating with who, which one? So it can be phone network, or it can be also email network. Okay, who is emailing which one? Okay, so that's also a big network. All right, now we can actually represent them using graph. Okay, so again, the set of users. Okay, if one user is communicating with another user, we can have an edge. All right, and in this particular example, we can see that we might want to use a directed graph. All right, so if we say that user A1 is emailing with user A2. Okay, so here we might have a directed edge to represent that. All right, so web network means the whole web network means it's a list of web page. Okay, now if we look at a web page, particular web page, you can see that one web page can have actually multiple other link that can redirect to another page. So in web network, you can see that if we have multiple pages, means each of the web page, they are the node. Okay, and if one page has a direct link from that can bring us from one page to another page, okay, then we can have an edge between these two pages. All right, so they are the node, and the edge means actually which page has a link to which page. Okay, so you can see that here also this is an example of directed graph. So social network, we have actually talked about social network. In social network, depending on the problems, we might want to represent them using both directed or undirected graph. So if we are only concerned about friendship, all right, so for that, we might want to use only undirected graph. All right, but if we want to use like following relationship, okay, who follows who? All right, so in that case, we might want to use a directed graph. All right, so let's talk about how to represent a graph. Okay, so represent graph means we talked about what is a graph. All right, but when we are as a computer scientist, when we're going to really write a problem, we're going to solve a problem using graph, how we can actually represent a graph. Okay, so there are two ways how we can represent a graph. Okay, so there are actually two ways. So the first one is the adjacency matrix. So adjacency matrix is going to look like this. Okay. So if this a particular graph, a graph is a set of vertex and edge. Okay. So each graph is a set of vertex and edge. All right. So in the adjacency matrix, we are going to represent graph as a matrix with dimension of size of V, okay, times size of V. For example, in this graph, we have 1, 2, 3, 4, 5 node. Okay, so to represent this graph, we're going to use a two-dimensional adjacency matrix with dimension 5 times 5. Okay, so here 5 means the size of vertex is 5. Okay, how many vertex or how many nodes we have? Okay, we have 5 nodes, so we are going to represent them. We're going to represent this graph as a 5 times 5, where we're going to represent them as actually a size of vertex times size of vertex, means it's a square vertex. Okay, I'm sorry, that means actually it's a square matrix. Okay, so the number of row and the number of column is going to be same, and the number of row and column is going to be the size of vertex or size of node. Okay, so all right, and here what will be the value of each cell? Okay, so the value of each cell Aij is going to be 1 if there is an edge between this pair of node. Okay, or 0 if we do not have any edge between this pair of node. For example, let's look at this graph. Okay, we have 5 node, so that means we are going to need a 5 times 5 matrix. Okay, now here we have to represent whether a node is connected with another one. Okay, so that's the most important part of the graph. We have to represent the connection between a pair of node. Now, if a pair of node is not connected, we are going to represent them as a 0. All right. For example, you can see that each value in this matrix Aij will be 1 if they are connected, 0 if they are not connected. So A to A is 0 because there is no edge from A to A. So we have a edge from A to B. So A to B will be 1. So A to C 0 means we do not have any edge from A to C. A to D 1 means we have an edge from A to D. A to E is 0 means we do not have any edge from A to E. All right. So mostly we're going to represent this graph using this matrix. All right. So let's actually redraw the same graph. We'll see that we can actually redraw the same graph using this matrix. So here you can see that this is a 5 times 5 matrix, and means we're going to have 5 node. Okay, so let's draw 5 node. Okay, so let's give them name A, B, C, D, and E. Okay, so we're saying that we have a edge from A to B and D. So B and D. So from B to we have an edge from A to D. So from B we have an edge from A, we already have that, and D. Okay, from C we have an edge from only D. From D we have an edge from A, B, C, and E. Okay, so we have an edge from A, B, C, and E. All right, so from E we have only edge from D, and we already have that. Okay, so this is actually the graph, and if you look at this graph, okay, this is actually the same graph. We have a cycle here, A, B, D, and D is connected with C and D. Okay, so this is actually the same graph. So you can see that we are actually, this matrix has all the information about this graph. Okay, so we can represent a graph using a matrix. And here you can see that it's actually two-dimensional matrix. Okay, so two-dimensional matrix, these are representing the row and these are representing the column. Okay, all right, and each of the value represent whether a pair of node is connected or not. All right. Okay, so if we have a undirected graph is always going to be symmetric. Okay, so undirected graph is always going to be symmetric because, I mean, if A and B value is 1, okay, then B to A value will be always 1. Okay, it represents that A and B are connected, and this value also represent B and A are connected. Okay, same for here, C to D is 1 and D to C will be also 1. So if we look at this graph, if the graph is an undirected graph, okay, undirected graph, and it is always going to be symmetric. Okay. Now, the directed graph represent is not going to be symmetric actually. The directed graph means, so in the directed graph, A is connected with B doesn't mean that B is connected with A. Okay. So for example, let's say this is the adjacency matrix where we are representing a directed graph. Okay. Here you can see that we can say that A is connected with B. Okay. But B to A is 0. Okay. So A to B is 1, but B to A is 0. Means that we have an edge from A to B. All right. All right. So this is not symmetric. Okay. So an undirected graph is not always going to be symmetric. All right. So if we have a weighted graph, so in this example, we had an undirected graph and unweighted graph. Means we're only representing whether a pair of nodes, whether they're connected or not. Now here, we have a undirected graph, but also this one is also a weighted graph. Means actually each edge has an associated weight. So in that case, actually, we're going to represent it like that. So the value of Aij, if I and j is connected, we're going to represent this as in with the value of weight. For example, here A and B is connected. Okay, so the value of this cell is going to be 8. All right, so A and D is connected, so the value will be 3. Okay, so 1 represent means actually all the value is 1 means actually whether only they are connected or not. But as each edge has an associated weight, we're going to represent this value with the value of weight. Okay, so here also, if you look at this matrix, you can see that this one is also going to be an symmetric matrix. Okay, symmetric, because actually, although we have weight, this one is actually undirected graph. So the weight between A and B is same as the weight between B and A. Okay. All right. So this one is one way to represent a graph. Okay. So another way to represent a graph is adjacency list. So adjacency list means in this graph, what do you want to represent? So let's say we have this graph here. We want to say that which of the nodes are connected with A, which of the nodes are connected with D, or which of the nodes are connected with B. Okay. Now, here in the adjacency list, we are going to represent the graph as a list of list. Okay. So we want to say that we have a node A, and A is connected with B and D. Okay. So A has a list of vertex with which A is connected with. Okay. So every vertex U belongs to the set of vertex contains an adjacency list of the set of vertex V such that there exists an edge UV. Okay, belongs to the set of edge. Now A is connected with B and D. So A will have a list like this. So A will have a list like this, B and D. So in this here, it doesn't say that B is connected with D. Okay, I mean, it doesn't represent that B is connected with D, although there is a connection between B and D, but it doesn't represent that B is connected with D. Okay, this is going to be just a list of vertex where A is connected with them. Okay, so for example here, A and D, this is actually a list of vertex. Okay, so this list of vertex which B is connected with. Okay, for example here, D is connected with A, B, C, and E. From this doesn't mean that C is connected with E. Okay, it doesn't represent any information like this. This is just a list of vertex. Okay, we're saying that A, B, C, E, this is a list of vertex, and D is connected with this every nodes in this list of vertex. Okay, all right. So you can also actually represent, you can also redraw, okay, restore the graph from this representation. For example, let's see, we have this adjacency matrix, okay? So we'll be able to visualize how the graph looks like. So you can see that we have these are the set of node, okay? We have this set of node here, A, B, C, D, and E. So we're going to look at the list of A. So A is connected with a list of A, B, D. That means A is connected with B and D. So B has a list. Okay. So in this list, we have two nodes, A and D. All right. So B is connected with A and D. So C has a list of node, only one node in this list, D. That means C is connected with D. So the list of D has this 4 node, means D is connected with A, B, C, E. So D is connected with A, B, C, E. And E is connected with D. So this is the graph we can find from this adjacency list. And you can see this is actually the same graph. Okay. Now, obviously, this adjacency list is going to look like if the graph is a directed graph. So you can see that A is only connected with only one node, B. Okay, so let's redraw actually from this adjacency list. And now we are saying that this is a directed graph. Okay, so we have here A, B, C, D, E, set of node. Okay, so we say that A is connected with B, and this is a directed graph, means the direction is going to look like this. So B doesn't have any connection with any node. Okay, means B, the list of B is empty. So C is connected with D. D is connected with A and B. So D is connected with A, and D is connected with B. And E is connected with D. Okay, so this is the graph we are talking about. All right. So if we have a if we have a weighted graph, okay, if we have a weighted graph, both directed or undirected, okay, both directed or undirected, we can actually represent them also using adjacency list. Okay, how we can do that actually? If or when we are going to represent a list of a particular node, we are going to also associate the value of the node with an edge, with an weight of the edge. For example, this list of the node A is going to look like this. Okay, so obviously here we can actually represent them like a structure or an object. Okay, where each of the node here, I mean each of the node will have a let's see, name of the node and the associated weight from A to B. Okay, so when A has a list of edge, B and D, okay, each of the node will also be and associated with the edge by which A is connected with this node. Okay, all right, so this is going to look like this. A has this list B and D. So B will be associated with the weight, okay, which is associated with A to B. And D will be associated with the weight by which A and D is connected. Okay. All right. Now in the next segment, we're going to talk about what is the difference between adjacency list and adjacency matrix. Means how do we decide what type of representative we are going to use. Is it going to be an adjacency list or adjacency matrix?